tomorrow. Maybe you want your parents to come tomorrow. Actually, if they don't want to come at all, I'm fine with that. And I won't be all right. So here we go. So up at the top, sine and cosine. So I apologize for the poor quality of this, but you know, that's okay. You've got it in your notes on this, but this is at least they're in one place. Maybe you can study a little bit for the other for the test. Just review it for yourself. Of course, the cosine graph starts up here. Domain, all reals, right? Range, -1 to 1. That's the part I was talking about. That we really got to understand that what comes out of sine and cosine is that. The zeros. Now, let's talk about zeros. Let's talk about a way of writing, because this fits in with what we're doing with our inverse functions and actually going into the next chapter. And you might have seen it on my Desmos graph when I was graphing down. It's not on that one, so I'll show you that in a minute. Okay, the period, of course, is 2 pi. What about the zeros? Well, the zeros happen at pi halves and 3 pi halves and 5 pi halves. They happen every pi units, right? Every pi unit you get a 0. Is that a big deal? Not a huge deal, but when it comes to the secant graph, it does. So it's not like I'm going to ask you a question, where are the zeros, and want you to write this down on this next coming test, okay? But looking to the future, you are going to have to do this. And so let me show you how we would write this, because there's an infinite number of zeros, so we obviously can't write them all down. But there's a pattern. It's 1 pi halves, 3 pi halves. It's every 2 pi halves, right? It's 1 pi half, 3 pi halves, 5 pi halves, 7 pi halves, 9 pi halves, right? And -1 pi halves, -3 pi halves, every 2 pi halves, or every pi, right? Added on or taken away if you start at this first one here, pi halves. Well, here's how we can write that. Pi halves plus pi times n, where n, now, did you do some of this in Algebra 2? Where we did something like this? Does that look vaguely familiar at all? Okay, doesn't matter. I didn't know if you might have done it in some domain ring stuff. But anyway, so what I'm saying here, where n is a member of the integers. In other words, n is a 0 or a 1 or a 2 or a 3 or a -1 or a -2 or a -3 to infinity. And so if you think about it, this is my first one, pi halves, plus any multiple of pi. So pi halves plus 1 pi would get you to 3 pi halves. Plus 2 pi would get you to the next one. Plus 3 pi would get you to the next one. Plus 4 pi, right? Just keep adding on pi. So this would be 1 pi, 2 pi, 3 pi, or it could go the other way. It could be -1 pi, or it could be 0. If it's 0, that just gives me this one, pi halves, right? Pi halves plus 0. If that's a -1, it gives me pi halves minus pi, which gives me this one, minus pi again, okay? So that's how we often write that, pi halves plus pi times n, multiples of pi, okay? Integer multiples of pi. All right, now where I did that and where that came into play for me on this scenario here was when I was doing the tangent graph, and I wanted to show these asymptotes. Well, the asymptotes for cotangent happen at 0 and at pi and at 2 pi. So what I did right here is I did pi halves plus, well, that was for tangent. Here I did pi times and then -2, -1, 0. I only needed a few, so I just did a list, and that multiplied. That's how I got like 5 of them there, all on this one. For tangent, they happen at, for tangent, your asymptotes are at pi halves, and then they go every pi. Let me get rid of that. So they're at pi halves and then 3 pi halves, just like our zeros are on the cosine graph. But they're pi halves and then multiples of pi. So I had pi halves plus, and then I just did that. Okay, it's the same idea. That's going to be something we will do a lot of later on. Okay, so don't be freaked out when you see it. Okay, again, sine, all reals, right? Domain, -1 to 1. Okay, again, where are zeros? They're at 0, pi, 2 pi, so they're every pi times n. So pi times 0 would be at 0. Now it's x equals, I should say it's x equals, right? X equals pi. Pi times n, so 1 pi, 2 pi, 3 pi, -1 pi, -2 pi, -3 pi. So And I'm not going to make you write n as a member of the integers every time. Just make that assumption. Okay, period of course is 2 pi. All right, go down to tangent and cotangent. So again, I've written the asymptotes there. Just what are they? All right. Yes. No, we're not going back. All right, asymptotes. So tangent and cotangent. So like I was just saying. So the asymptotes, where are the asymptotes? It would be good to write that up there. Pi halves, 3 pi halves, 5 pi halves, right? They're every pi units for the asymptotes. And I went ahead and put in the 0 plus pi n. But that's, I always like to write the first one and then plus whatever multiple they're repeating. Okay, and so even though you don't need that 0. Okay, so the domain. So what about the domain? So the domain gets tricky here. It's all reals except where the asymptotes are, right? So all reals, but x can't equal pi halves plus pi n. Okay? In other words, x is not part of the domain, but you can't list, you can't sit here and list all the places that it's undefined because it's infinite. And so that's why you need this pi halves plus pi n. You need a way to say all of those places where it's undefined. So it's all reals except those values. The range is what? For tangent. All reals. Okay, because the y values are all reals. Okay, zeros. Now where do the zeros happen? The zeros are where it crosses the x-axis. Well, that's at 0, at pi, at 2 pi. How would I write that? They happen every pi and they start at 0. 0 plus pi times n, or just pi times n. And that's x equals, right? Those are x values where the 0 is. And the period, of course, we said was pi. Okay? So the domain on cotangent is all reals, except where the asymptotes are. Where the asymptotes, they are same place the zeros are on this one. The asymptotes start at 0 and go every pi units. So x cannot equal 0 plus pi n. All those multiples of pi. The range, again, is all reals. The zeros are where the asymptotes of this one are. The zeros are at pi halves, 3 pi halves. So the zeros are at pi halves plus pi n. And the period, of course, again, on that one is pi. So, okay, again, I'm not going to ask you the question where you have to put in that pi halves plus pi n kind of thing on this test, okay? What you need to know is the basic shape, the direction it goes. You need to be able to stretch it, compress it, and so forth. Okay, and then finally the secant and the cosecant. Remember, secant's a reciprocal of cosine, so you first draw in your cosine graph, and then you put the u's on. Okay, so the domain is going to be all reals except those places where cosine is 0, where those asymptotes are, right? Well, that's at pi halves, 3 pi halves. Again, it happens every pi unit, so x cannot equal pi halves plus pi n. Okay, the range is what? Yeah, it's, you might say negative infinity to -1 and 1 to infinity, but it's, and actually be greater, you could include -1 and you can include 1. Or you could say all reals, but y can't be between -1 and 1, right? All reals, but that space from -1 to 1, kind of the opposite of, okay? But that's a good way to do it. The period is 2 pi, just like it is with cosine, and there are no zeros. There are no zeros. It never crosses the x-axis. Okay, same thing here. All reals is the domain except where the asymptotes are. The asymptotes are at 0 and then every pi unit, so 0 plus pi n. X cannot equal 0 plus pi n, right? Because there are asymptotes there. The range is the same, negative infinity to -1, 1 to infinity, right? You can't be between -1 and 1. There are no zeros. Periods 2 pi. Okay, so just the basic elements of the 6 trig functions, but more importantly, be able to graph them, be able to stretch them, compress them, shift them. do all that kind of stuff, okay? So that'll be a big part of the test, just like the quiz we just went over was with sine and cosine, so there'll be some repetitive parts of that. Here's a graph, write the equation, here's an equation, draw the graph, okay? Those kind of things will be a big part of it. All right, so now let's turn our attention to the stuff from last week, the inverse function stuff. Okay, and then we'll talk about the homework. The homework was a little bit like what the test would be. I'm leaning right now towards the whole test being no calculator. I mean, I'm not that interested that you can punch in second cosine 0.75. I know those would be nice, easy questions for the quiz. Maybe put a couple on there. Bonus. Bonus. Yeah. I mean, you know, chances are a good portion of it, if not all of it, will be no calculator. All right. So inverse. So there was, but it is still important to be able to properly type in your calculator when we get into calculator problems that we want to solve that way. So we need to be able to do it. And that's where that section you have on today's homework came in, where just can you do that? Where you get any weird things, we can talk about it. But then that's about it for that. So back to where I started the discussion of inverse functions with the parabola. So you got x squared, you got square root of x. Okay, and so all right. So we've got those two. Those are inverse. This clearly, the blue one is not a function, right? So we talked about having to restrict the domain of that so that we could get it to be a function. So let's take x squared and let's only look at this part of it. Remember, we were saying if you look at this part, it passes the horizontal or fails the horizontal line test. So if a function fails a horizontal line test, when you flip it, okay, and do the inverse, it's going to fail the vertical line test. So what we want to do is we want to restrict it. So we restrict it to just that part of the parabola, and then we get our square root function. Okay? And then that is okay. So we're going to talk about square root and square root of x. So if you want to go back to your notes here, no, that's okay. Never mind. We don't have to go back to our notes yet. So we've got that. All right. Now let's apply that to sine and cosine. Okay. So here's a sine function. Clearly fails a horizontal line test. When you plug in pi 6, you get out 1/2. You plug in 5 pi 6, you get out 1/2. You plug in 13 pi 6, you get out 1/2. You know the pattern. You plug in what's 17 pi 6, you get 1/2, right? You just keep going and going, and you can get out 1/2. Well, what do we do with inverse functions? We interchange the x and y. So now all of a sudden, pi 6 1/2, 5 pi 6 1/2, 13 pi 6 1/2. Now all of a sudden you flip those around. Now it's 1/2 pi 6. 1/2 5 pi 6, 1/2 13 pi 6. You can't have that. You can't plug in a 1/2 and get out all these different things. You can only get out one thing. So we have to restrict the sine graph. So we don't want all these different values. So what we have to do is we have to take our sine graph and we have to restrict it. And so it's only going to be, so we're only going to look at the sine graph for that one little piece right there. And that's from negative pi halves to pi halves. First and fourth quadrants. Negative pi halves to pi halves. First and fourth quadrants. And then there is the arc sine. There's the inverse then of those. And so it passes at the vertical line test and so forth. All right. So with that introduction, let's go back to what we were talking about last week. So very important that we understand, probably the most important thing in dealing with these inverse functions is what kind of thing goes in and what kind of thing comes out to these functions. If you keep this straight, then this is going to be a big help to you. Okay, so let's look at the basic sine function that we've always worked with and are comfortable with. What do we plug into the sine function? We plug in angles. We plug in sine of 30 degrees. We plug in pi 6. We plug in pi halves. We do those kind of things. We can plug in anything. All reals is our domain, right? We just got done doing it on that worksheet. All reals is our domain. We can plug in anything. What do we get out of the sine function? We get what I call values. Values. Now you can say 30 degrees is a value, pi 6 is a value. No, those are angles. We're talking about those as angles. What you get out are values from the sine function. you get values from -1 to 1 out. Now, when we go to the inverse trig function, what happens? We interchange the x and y, right? That's what happens when we go to an inverse. We interchange the x and y. So therefore, when you have arc sine or sine -1, either one of those, sine inverse or arc sine, they're the same thing. I just use them interchangeably. I really prefer arc sine. What's going into that? That's got to be values, right? That's got to be -1 to 1. If you can remember that, that's going to really help you, because on the test, no calculator, what if I give you this problem right here? What if I tell you to tell me the arc sine of 2? What are you going to say? Not possible. Yeah, whatever. Does not exist. No solution. There is no value. And why will you know that? Because you'll say to yourself, all right, the sine function, you get out -1 to 1, so the arc sine, you put in -1 to 1. We're interchanging the x and the y. So we all know, hopefully, the normal sine function, we put angles in, we get these out. So for arc sine, it's a reverse. We put in -1 to 1 values, and we get out. Now the problem is, what do we get out? We get out angles. Well, here's where we had to restrict. Because you could get out pi 6, or 5 pi 6, or 13 pi 6, or 17 pi 6. You get out an infinite number. We can't get out an infinite number. We only want 1. When we type in arc sine of 1/2 into our calculator, it's only going to give us 30 degrees. Now, I will say in the directions, give all angle answers in radians in terms of pi. Okay, so I'll give you nice values. And so will be important to know the unit circle? Absolutely. The unit circle. Now, you can do it with triangles, and we'll talk about that here when we look at the homework. Okay, so this is going to be angles from -pi/2 to pi/2. Coming out are angles, but they have to be restricted. Now, in the sine graph, we don't have. We can put in any angles we want, right? We can put in any angles we want, and we get out values from -1 to 1. However, when we go to the inverse trig function, we put in values from -1 to 1. We get out angles, but they have to be between -pi/2 and pi/2 for sine. Okay, we're going to write this down for the other ones here. Okay, so you've already kind of written that down. Okay, so you've already sort of written it down for sine. I guess if you want to write it. Okay, I thought I would take a little bit of time here. Today, I thought after Friday it was important that we really go through this and talk about it. Okay, so our normal sine, I don't know if you have to write this, because I think we already should know that, but I think maybe having it and putting it right next to arc sine isn't all bad. Okay, so y equals sine x, you put in angles, you get out values. What's the domain? We just did it on that other sheet. It's all real. Sine, you put in anything. What do you get out? You get out values from -1 to 1. Here's the sine graph, right? Okay, here's arc sine. Okay, now we're not going to take time to do the cosine, the tangent ones right now. Okay, but I can put them up later, or they'll be in the video. I'll just go to them, and you can go to the video, and if you want to write it down, you can. Okay, but again, we want to go on, but you'll get the idea. Okay, so there it is. Okay, so here's what does arc sine look like? That means we're putting values in, we're getting angles out. Remember what I told you, when you see arc sine, you should say to yourself, the angle whose sine is. So if it's arc sine of 1/2, you should be saying the angle whose sine is 1/2. The angle whose sine is 1/2. You're getting angles out, values in. So your domain is -1 to 1. Your range are angles. They have to be between -pi/2 and pi. Here's what the graph of it looks like. Now, if we continued it, the red, it would just continue going up and down, but we just have this part of it. Domain -1 to 1, range -pi/2 and pi/2. Okay, just quickly here, I'll put it up here, and then on the video if you want to get it, but the only difference here is this one goes 0 to pi. Okay, this one we restrict 0 to pi. Okay, we only look at this piece right here from 0 to pi. Okay, 0 to pi. First and second quadrants. Okay, that's our cosine. Put in values negative 1 to 1. Now, what about tangent? Okay, tangent. We already talked about asymptotes. We already did all that. Y is all reals. Okay, here's your tangent graph. Clearly, that fails the horizontal line test. We're going to flip it. We only want one branch. It's this one right here. Okay, so we flipped it. We saw that in the graphs on Friday. That's your arctangent right there. That's this branch right here flipped over. So what is that? That's negative pi halves to pi halves, just like sine. So sine and tangent are restricted negative pi halves to pi halves. Cosine is 0 to pi. Okay? You can put anything into arctangent though, right? We said arcsine. If you do arcsine of 2, you say it doesn't exist. Can't do it. But tangent's okay. We can put anything in, right? We can put anything into arctangent. We can have arctangent of 2, arctangent of 20, arctangent of 30, right? We can, right? And we're going to get out answers somewhere between negative pi halves. Okay? All right. So what questions do you want to look at in the homework? Let's do the first section first. What was it, 5 through 20? Aren't those all just unit circle things? That's all they are. Now that's going to be that'll be a big part of the test, to be honest with you. Okay, that'll be the number one thing that we will use arcsine, arccosine, arctangent for. Okay. Now there weren't any arcsecants or anything like that, right? Okay. So and I don't know if we'll get into that. If we're going to, we'll look at it tomorrow. Okay. So let's talk about how you do one of those. Let's just do a simple one first. If we got arcsine negative 1/2, okay? Raise your hand if you're thinking of the unit circle. To me, it's unit circle or triangles. Those are your choices. How many are doing unit circle? How many are doing triangles? Okay. Now, it doesn't surprise me because we made such a big deal about the unit circle early on, and that's good. And so you got it. So now, the key though on the unit circle is what quadrant we going to. What quadrant are you going to? We got to go to 4. Remember, the thing you got to remember about negative, about arcsine, in goes values, out comes angles. The angles have to come out between negative pi halves and pi halves. Okay? So, sine is negative. It's positive up here. It's negative down here. So, what angle is that? That's a 30-degree reference. Now, I'm going to want your answers in radians. I don't know what the homework said. It just said evaluate without a calculator. I would tell you angle answers in radians in terms of pi. So this is a 30-degree reference, okay, for this to be 1/5. So the answer to this should be 11 pi over 6. No, that's wrong. That's not between negative pi halves and pi halves. It is negative pi 6, right? 11 pi 6 would be going this way. So the answer needs to be negative pi 6. If you did it in degrees, you'd have negative 30. If you typed in your calculator, you weren't supposed to. I don't even know if that's one we had. So let's do one we had.
First one was just off.
Yeah, first one was just arcsine 1/2. And that would be pi 6. Did we do the odds or all of them in this section? We did all. Okay, so any of them, any other question? Anyone that you're tricky? Yeah, 11. Arccosine. And that was negative root 3 over 2. Is that right? So inverse cosine, arccosine, same thing. Okay. So which quadrant are we going to? 2. Arccosine is between 0 and pi. It's the only one. Right? 0 and pi. So we're going to go for negative values. We're going to go over here. Where's root 3 over 2? What angle gives you cosine root 3 over 2? The x value. Isn't that pi 6 also? Is that a pi 6 reference? It's down here at 5 pi 6. Okay? So the answer to this is going to be 5 pi 6. Okay? Now, you can do it as a triangle. Now, you still got to know the same stuff. You got to know that it's in quadrant 2, so you got to know where to draw your triangle. But now, the reason I like triangles is it's cosine. Oh, that's the x. So I know that's got to be negative root 3 over 2, which means this has to be 1/2, which means this has to be 1. Across from the 1/2 is always the 30, right? So I like triangles from that standpoint. Right? I like triangles from that standpoint. Okay? But if you remember it without that, using the unit circle, that's fine. So this is 30 degrees or pi 6. And so we're going to go there. So 5 pi 6 is your answer. Okay? All right. What about 20? Arc cosine of 1. Inverse cosine of 1. What's that going to be? The angle whose cosine is 1? 0. It's right there. Right? 0. What if that had been negative 1? The angle whose cosine is negative 1. Radians. Pi. Okay. 180 degrees or pi. Okay? So yeah, so that's just, so that shouldn't be bad, right? That's just asking in a different way. Well, here's what we did on the quiz while we were doing that. I said cosine theta equals 1. And then you just had to tell me what theta is. It's the same thing. It's the same thing. Or negative 1 in this case. Now that I changed it. It's the same thing. Same problem. Okay? So that standpoint, that's one of the main things we have to do with the inverse. Okay? All right. Let's see. And then the other ones with the calculator, I don't think those are probably an issue. You just type those in. Okay. All right. So do those real quick. Do those real quick. Let's check ourselves on, see how we're doing. Triangle or unit circle? Okay, a lot of you look like you're. Now, so, a lot of stuff, and it's important, all that stuff about the inverse function and interchanging x and y, and so then we're gonna add on to it the whole thing of restricting the domain and so forth. It's gonna be important, but when it comes to the actual problems you'll have to do on the quiz, I think they're gonna be in really 2 categories. One is this, and then the other is the other thing we're gonna do today. Okay, and we're going to add to it. So arc sine root 3 over 2. So again, when you're doing these problems, really the only thing you have to think about with that restriction is it negative pi halves to pi halves in my first and fourth quadrants, which is arc sine or arc tangent, or am I 0 to pi, which is first, second quadrants, which is cosine. Okay, so this one, root 3 over 2, I'm being quadrant 1. The root 3 over 2 is the y because it's sine. That's a 60-degree reference. That's going to be pi thirds. Okay, this one, negative root 2 over 2, since it's our cosine, that puts me in quadrant 2. The cosine is the x, root 2 over 2, root 2 over 2, that's a 45-degree reference. So that's going to be pi fourths, that's going to be 3 pi fourths. Okay, good? All right, And that's, again, doing it with triangles. If you got your unit circle there, that's good too. Arc tan root 3, now that's sometimes a little trickier, but I know that triangle, that's when I have negative root 3 over 2 over 1 half, because the 2's in cancel, right? Negative root 3 over 2 here, 1 half here. When I put opposite over adjacent, that's going to give me negative root 3. Remember, tangents like sine, first and fourth quadrants, negative pi has pi. That's a 60-degree reference, so that would be negative pi thirds. Negative pi thirds, not 5 pi thirds. Arc sine negative 1 half, the one we did earlier when I said 11 pi 6 like that. Okay, arc sine negative 1 half, so it's in the fourth quadrant. Sine's a y, negative 1 half, that'd be root 3 over 2. That's a 30-degree reference. Negative pi 6. Okay, so going to be a handful of those on the quiz to do with unit circles. We'll do them in radians. We'll give exact answers, no calculator. All right, so let's talk about this. So new thing for your notes. Composition of functions, putting a function inside of another function, okay? Putting a function inside of another function. We're going to do that with the trig functions and the inverse trig functions. Now, you may wonder why, and to be honest, if you've taken calculus, you will get to see why, because this is always a lesson that I end up having to do again in calculus about this. Because these inverse functions, it matters in some things we do in calculus. Okay? So, I just give, above the line here, I've just given the example of, a couple of basic functions. So I got an x squared and an x plus 4. So that's my f and g functions. If we do f of g of x, what's that mean? But what would we do first?
X.
So if I said, so if I said to do f of g of 3, what would you do first? You'd plug a 3 into the g function, you'd get an output, and then you would take that output, it would become the input for the f function, right? And then you would get your final output. So your final output's going to come from the f function. Now, if I just say f of g of x, then that says take the g of x function and plug it into the f function for x. So that means take the x plus 4, right? Take the x plus 4 and put it into there for x. So what are you going to have? You're going to have x plus 4 quantity squared, correct? Now reverse that. Now do g of f of x. Does it make a difference? It does. It absolutely does. Which one you plug into first, it makes a big difference, right? And so here, this says take the f function and plug it in. Let's do that in blue. Take the f function and plug it in to that function for x. So we're going to take x squared and we're going to plug it right there and we're going to get x squared plus 4. Well, those two things are very different. Those two things are very different. Okay? So all I'm trying to show you with that is, number one, remind you about composition of functions when you put a function inside of another function. And order matters. The order that you put one into the other matters. Okay, now let's apply this to inverse functions. Okay? So now let's apply this to inverse functions. So let's say we had the function f of x equals x squared. And its inverse, which is the square root of x. Now, I showed you those graphs earlier with the parabola x squared. I said, let's restrict it to just the right half of the parabola. And then the inverse would be the sideways parabola, just the top half of a sideways parabola. Okay? So that's the inverse function. So f of x is x squared. And I'm not going to call it g. I'm going to call it f inverse. Right? Just like we have our sine inverse, our cosine inverse, so forth. You know that's where we're going with this, is to do it with sines and cosines. All right. So, again, the order matters. If I put the inverse function into f, or I put f into the inverse function, the order is going to matter. All right? So, it looks like this. If I take the inverse function, square root of x, and plug it into f, I would get the square root of x all squared. Now, your intuition is probably telling you that that's going to equal what? The square root of x squared is going to equal x. is what you would probably think, right? Makes sense. Okay, now let's talk about doing it the other direction. Let's take f, the x squared, and let's plug that into the inverse function. Let's take x squared and plug it into the square root function. We get square root of x squared. And again, your intuition probably is telling you that that's what? That's x. Well, turns out in one case you're going to be right. In the other case, you could be wrong. Okay, it may not be x. All right, and why or how can that be? Well, let's look at a couple of quick examples. Okay, let's start with this one in red right here. Now, notice we're doing the square root first, right? So what is square root of 9? 3. And then take 3 and square it. What do you get? 9. Everybody's all, you're all waiting. You're ready. Well, I think it's 9, but he's trying to trick me. I can tell. So yes, it's 9. So sure enough, you got back what you started with, right? Okay, let's try with a negative 9. What's square root of negative 9? If we're talking about the real numbers, it doesn't exist, right? But you guys did imaginary numbers last year, didn't you? Remember the I? Yeah. Let's just do that real quick. So what is square root of negative 9? 3i, right? Because I was square root of negative 1, right? So it's 3i. What's 3i squared? 9i squared. What was I squared? Negative 1. What's 9 times negative 1? So it worked. We got back what we started with. So it would seem that square root of x squared would indeed equal x. It seemed to work in both those cases. Now, let's try it the other order. Let's start with a 9. What's 9 squared? 81. What's the square root of 81? 9. Now remember, don't say plus or minus, right? Plus or minus is if we're solving this equation right here, x squared equals 81, then it's plus or minus 9, because either one you could put in for x and it would work. We're just saying the square root of 81. The square root of 81 is 9. So we got back what we started with. Good. Let's try it with a negative 9 in there. What's negative 9 squared? 81. What's the square root of 81? We did not get a negative 9 out. That's because of the restriction. And that's what's going to happen to you with these sine and our cosine things. The order matters. Now going this way, no problem, because there was no restriction on x squared. Okay, it was fine. Okay, but here we had an issue. Okay, I've got a fancy calculator here that we use in calculus, and it actually knows this. And when I put in, come on, hurry up. I don't have time for this. I don't have time to get that smart. Okay, so bottom line is the square root of x squared does not equal x. The square root of x and then squared does equal x, because look at this. Wait. Come on now. Come on, there we go. If I put into this calculator the square root of x squared and hit enter, it's that. Because you can only get a positive out of a square root. If the last thing we do, see, if f inverse is on the outside, and that's the square root function, if the last thing we do has a restriction, then we may not get back what we started with. And the restriction on square root is you're always going to get a positive. Square root of x, you're always going to get positive. So if x starts out negative and you end up doing square root, you're going to get out a positive. Not the negative 9 you started with. Okay, bottom line is our order matters, and the restrictions are going to come into play. So what's going to happen is we're going to take our trig function and our inverse trig function, and we're going to look at those. Okay, and what happens when we do one way or the other. In this case, I got the sign on the outside. In this case, I got the inverse sign on the outside, and what happens. And we're going to look at some examples of that. Okay, all right. Thank you.
Organized.
So I went ahead and printed for you because I felt like some of you were trying to get those notes down, and I didn't, and I was kind of rushing you through that. So I printed this section here about the trig, the sine, cosine, tangent, arc sine. Okay, domain, so you got that to look over. Okay, so again, the key part of it's this blue part up here. Okay, that we understand that again, when we put into sine, we're getting angles, and we get out values. So on the arc sine, we put in values, we get out angles, and the values, of course, especially on sine and cosine, that's important because there's always between -1 and 1. Okay, now in tangent's a little different. We can put in anything, we get out any values, so we can put in any values. But the angles we get out are restricted. So what we get out of the sine of the inverse trig functions is always restricted here. Okay, in first and fourth or first and second quadrants, depending on which one we're doing. Okay, so we were just talking about this thing with the square root. We were basically, what we got out of this is the order matters. The order that you do them matters, okay, because of the restriction, and that's where that 0 to pi thing and all that comes in. So let's see what some problems look like. So this is where the rubber really hits the road here. Anybody ever heard of it? But anyway, so let's take a look at this. So what if I write the sine on the outside? Now I'm going to do the ones that go together, like sine and arc sine, sine and inverse sine. We'll do that first. Those are the easiest ones, and then we're going to see what happens if we mix and match. So if these two are inverse functions and we put them together, they should cancel each other out, right? Think about what I've got up there. Sine of inverse sine should be like square root of x squared, which was x, sort of. It was x, but we had to be careful. There might be a restriction. But they should cancel each other out. Sine and inverse sine, cosine inverse cosine, tangent inverse tangent. But the order we do it's going to matter. In a minute, we're going to do it with the inverse on the outside and see what happens. But for right now, let's do it with the regular trig function on the outside. Now, my question for you is this. Is x an angle or a value in this example? In these three that I've written. X is a value. Remember, the arc sine, for a regular sine function, we put in angles. For the arc sine function, we put in values. So this x is values, right? Now that means those numbers here have to be between what and what? -1 and 1. So x here is going to have to be between -1 and 1. X here is going to have to be between -1 and 1. Now right here, x could be anything, right? X could be all reals because this is our tangent, right? X could be all reals down here. But for arc sine or cosine, this number in here is going to have to be between -1 and 1. Now, it turns out that this is always going to equal just x. This is the way that it will work nice, and they will always cancel each other out, and we don't have to worry about restrictions. Think about an example. If this in here is a value, let's say it's 1/2. What's the inverse sine of 1/2? What's the inverse sine of 1/2? What's the inverse sine of 1/2? Pi 6, right? The inverse sine of 1/2 means the angle whose sine is 1/2. It's pi 6. So if this is a 1/2 in here, inverse sine of 1/2 is pi 6. What's the sine of pi 6? 1/2. See how they cancel each other out? See how they cancel each other out? What if this is root 3 over 2? What's the inverse sine of root 3 over 2? Pi thirds, 60 degrees. Pi thirds. What's the sine of pi thirds? Square root of 3 over 2. You see how we get the same thing we started with? We started with square root of 3 over 2. We get back square root of 3 over 2. What if this is a -1/2 in here? What's the inverse sine of -1/2? Negative pi 6, right? We've been talking about that. Be in the fourth quadrant. Negative pi 6. What's the sine of negative pi 6? -1/2. See how they're canceling each other out, right? So sine, inverse sine cancels each other out. We just get x. When the sine or the cosine of the tangent's on the outside, that's what's going to happen. Okay? Those two are just going to cancel each other out. All right. Now, what happens when we reverse it? Now, in this case, is x an angle or a value? Now x is an angle. We're doing the sine of x. So like pi 6. Okay? So let's try this. What is the sine of pi 6? Remember, you always start on the inside of these functions, right? What's the sine of pi 6? 1/2. What's the inverse sine of 1/2? Pi 6. Aha, that worked. Seems fine. Okay, let's try this. Let's say x is 5 pi 6. What is the sine of 5 pi 6? What is the sine of 5 pi 6? 1/2. What's the arc sine of 1/2? Pi 6, not 5 pi 6. You see what I mean? We didn't get back what we started with. Just like the square root example. We started with -9 down here, but we got out 9. Okay? It's because of that restriction. Why? Because I put in 5 pi 6, and what quadrant is 5 pi 6? Second quadrant, right? 5 pi 6 is second quadrant. But then we had to do the arc sine. What quadrants is arc sine restricted to? 1 and 4. Do you see the difference? So if I give you the arc sine of the sine of 5 pi 6, those are not just going to cancel each other out and give you 5 pi 6. The answer to that is going to be pi 6. So when the inverse trig function is on the outside, if you want to make a little note to yourself, when the inverse trig function is on the outside, that's when we have to worry about the restriction. This is the scenario when we have to work. But it's not like you have to memorize that. Not like you have to sit there and study, okay, when the inverse function is on the outside, I got to remember. Just think it through and you'll be fine. If I give you the arc sine of 5 pi 6, you just work it from the inside out. You say, okay, sine of 5 pi 6. Okay, 5 pi 6 is over here. That is 1/2. What's the inverse sine of 1/2? We just got done doing those problems for today, right? We did them. We had some up earlier. We've done this. What's the inverse sine of 1/2? Oh, inverse sine of, okay, inverse sine. That's negative pi halves to pi halves. That's quadrant 1 and 4. Sine of 1/2, okay, that'd be here. Okay, that's going to be pi 6. There's my answer, right? Like that. So it's not like you have to memorize that that's going to happen. Just like here, you don't have to memorize you're going to get this out. You just go, okay, sine of inverse sine. If you're given this problem, right here, you do inverse sine of 1/2. Okay, inverse sine of 1/2, that's going to be quadrant 1. That's going to be pi 6. Okay, what's the sine of pi 6? Oh, yeah, that's 1/2. So it's not like you have to memorize, oh, if it's in this order, do this. No, you just start on the inside and just do it, right? But that's where that restriction comes in. All right, so we're going to have some problems like this, so let's just look at a couple here. All right, so let's go through a few, and you guys I know have to leave whenever you have to go, just go. So tangent of arctan -5. I mean, Fad, I know you're not bad, so don't try to do that.
I think you.
Tangent of arctan -5. Tangent of arctan of -5. Okay? They should cancel each other out, right? And like I said, you don't have to memorize it, but if you do, that is real helpful in this problem. What's the answer? The answer is -5. When we do it in that order, arctan of -5, now that's not a nice value that we know. We're going to talk about here in a minute how we can draw triangles or something like this, and that'll make this even a little easier. But for right now, we just say, okay, arctan of -5, that'd be some angle, right? And the angle whose tangent is -5. So that's what the inside is, the angle whose tangent is -5, and then we want to do the tangent of it. Well, that's got to be -5. The angle whose tangent is -5, and then do the tangent of that. It's -5. Okay, what about this one? Now it's in that other order. We got to be careful. But even if you didn't think about it, you just do sine of 5 pi thirds. Where's 5 pi thirds? Quadrant 4. It's down here with a pi thirds reference, right? It'd be 1 pi short of 6 pi thirds. Okay, so it's down here. Now we want to do the arc sine of that. We want the angle whose. So what would this be? 1/2 down here, negative. No, that's for 3/2. Yeah. Just saying if you're still paying attention. All right. So that's I know you're not. So this is here. So look, sine of 5/3. So here's 5/3 down here, right? Fourth quadrant. Sine -√3/2. So if you wanted to, you could say, okay, this is going to be -√3/2. You don't even have to write that in there. I don't care. What's the arc sine of -√3/2? Well, it's this angle right here. But we're not going to write 5/3, are we? What are we going to write? Why?
Because it's a restriction.
Because we have to be restricted between negative pi halves and pi halves. We're in the right quadrant. We're in the fourth quadrant, and that's good. But we're not going to write it 5/3. We're going to write it negative pi thirds. Okay, because of the restriction. So when the arc sine or the inverse function's on the outside, that's when that comes into play.
Whatever going third quadrant.
Yeah, it could have. I could have given you 4/3. I could have done this problem as 4/3, right? So where would that have been? That would have been down here.
What about the angle that we actually use?
No, because the restriction for arc tangent is first and fourth. But I might give you one that's 4/3, which is over here, right? And so now you might be looking, yeah, no, that's a really good question, because if I would have given you this problem as 4/3 now, you'd have been down here. Well, you said, well, that's 4/3, but, you said, well, I got to go backwards. No, that'd be -2/3. That's not right either. Here's where you have to say, okay, the angle they gave me is in the third quadrant, but I know arc sine has to be in the first or the fourth. So you have to take this same triangle and you have to move it down here, right? And then you would say, okay, that's going to be -pi3. Okay? Let's try that on your calculator real quick. This is, what is this? This is 300. Okay? This is 300, right? So sine of 300. So do the sine of 300 in your calculator. Okay? Do the sine of 300. That'd be 5/3. Sine of 300, what do you get? -0.866, right? Which is 3/2. Now do second sine of that. So go second sine and then hit second answer. That's the quickest way to do that. What do you get? -60. Okay, now let's do 4/3. That's 240. Do sine of 240. What do you get? -0.866? -3/2. Now do the inverse sine of that. What's going to be the same thing, right? So inverse sine, calculator doesn't know you did 240 or 300. You're doing inverse sine of the answer, -60, right? So we get -pi3 either way. Okay? So if it draws it, if it puts us in the second or fourth quadrant, we're going to have to move it to the first or fourth, because that's what those restrictions tell us to do. Okay? All right, let's look at this one. Cosine of the inverse cosine of pi. Cosine of the inverse cosine of pi. Now I've tricked you. I've tried to trick you. Don't be typing your calculator. Cheater. What do you got? Domain here. What goes in? What's that pi? Angle or value? What's supposed to go into inverse cosine? Values. Remember, pi is just a number. Pi is just 3.14, right? Pi is just 3.14. Now, you think it's an angle when you see the pi, right? Now, would I do that? Probably not more than once, but I might, because I want to emphasize to you that you've got to think about what goes into these. The regular cosine function, you put in angles. The inverse cosine function, you put in values. And what do those values have to be between? -1 and 1. If you're doing inverse cosine, the value you put into it's got to be between -1 and 1. So this one would be an automatic, does not exist. No solution. Because you cannot put in something here that is bigger than 1 or -1. Okay? All right. And then this one. Cosine of pi3. See, that's not going to be a problem. It's in the first quadrant. So pi3 is here. Cosine of that is 1/2, right? Cosine's the x. And then what's the arc cosine of 1/2? pi thirds. So here, sometimes they do just undo each other, right? When the inverse trig function's on the outside, you might run into that restriction, but if it's already a first quadrant angle, that's good. That's what we want it to be, okay? And so that one is going to just undo itself. Okay, so what happens if we mix or match? So that, oh shoot, I have, okay, one more, not this one. Let's do this one. Arc cosine of the cosine of 3 pi halves. So I'm not tricking you, this is cosine, into cosine goes angles, this is an angle, okay? Is this going to just cancel itself out and give you 3 pi halves? I'm guessing not, right? Because, well, first of all, what's cosine of 3 pi halves? It's a good way to do it. What's cosine of 3 pi halves? It's down there, right? What's cosine there? 0. So this is now saying the arc cosine of 0. Now remember how we say that to ourselves? That's the angle whose cosine is 0. What angle has a cosine that is 0? Well, this one. But what else? Up here, too. Which one's it going to be? Where's cosine restricted? Where's cosine restricted? 0 to pi. First or second quadrant. 0 to pi. So we don't want 3 pi halves because that's not between 0 and pi. So this is going to be pi halves. You can try it on your calculator. Do arc cosine of 0. Do second cosine of 0. See if you don't get 90. Right? You get 90, right? Okay, arc cosine of 0. So 3 pi halves. So they, sometimes they do when the inverse function's on the outside. Sometimes they do. Okay, so that'll be the one that where you'll have to think about that restriction. Okay, and we'll be doing it without a calculator. Right? Homework you can help check, but you got to be able to do it without. Okay, what happens if we mix or match trig functions? If we mix and match them, in other words, we don't do a sine with an arc sine or a cosine with an arc cosine, what happens if we mix or match? Well, we draw a triangle. We draw a triangle. Let me show you what this means. Now, we're going to keep this simple. We're always going to keep the regular trig function on the outside, so we don't really have to worry, right? All we have to do, the only part of this we have to worry about the restriction is we just have to draw it in the right quadrant. Just have to draw a triangle in the right quadrant. Okay, so here's what one of these problems would look like. So I got tangent and inverse cosine. Well, they're not gonna undo each other. It's kind of like having x cubed and a square root. They're not inverses. They don't undo each other, right? So that's what's going on. So when you see one of these, so you see a mix or match, right there. Draw a triangle. So here's how this looks. You say to yourself, all right, self, the angle whose cosine is negative 2/3. Excuse me, positive 2/3. Now, what quadrant do I have to draw that in? Positive value. So I'm either going to be first or second. Which one? First. Second would be for negatives, right? Cosine is negative in the second. So the angle whose cosine is 2/3. Now here's where SOHCAHTOA comes in. SOHCAHTOA comes in here. How's cosine going to be 2/3? Adjacent over hypotenuse. Because 2/3 obviously is not one of our special values that we know about. Square root 3 over 2, root 2 over 2, those kind of things. So we're going to do that. Now, they want us to do the tangent of that angle. We don't know what this angle is. We have no idea. But we don't need to know because they want us to do the tangent of that angle. Well, how do we do the tangent? Oh, opposite over adjacent. Hypotenuse? Total. Total. Opposite over adjacent. How do we get this? 3 squared minus 2 squared. And then the square root. Right? We got to take the hypotenuse squared, Pythagorean theorem. So we got to take 9 minus 4, which is 5. So isn't this side going to be square root of 5? Right here. So what's the tangent? Square root of 5 over 2. Just like that. When you mix and match your trig functions and inverse trig functions, draw a triangle. The angle whose, this is why it's important to read that, the angle whose cosine is 2/3. So draw a triangle and make the cosine be 2/3. The tangent of that is going to be opposite over adjacent. Let's do another one. You guys try this one. Cosine of the arc sine of negative 3/5. Cosine of the arc sine of negative 3/5. on the inside, the angle whose sine is negative 3/5. The angle whose sine is negative 3/5. If we do no calculator on this, you'll have to do no calculator with your Pythagorean theorem too. So you have to do a little squaring and subtracting on your own. I don't care about simplifying the square root, so don't worry about it. What quadrant you in? Got to be in 4, don't you? Arc sine is either going to be in 1 or 4. Negative 3/5. So what's this side here? 5 squared minus 3 squared. 25 minus 9, 16. Oh, it's 3, 4, 5. Okay. So what's the cosine of that? 4/5. Makes sense in quadrant 4. Makes sense it's going to be positive. Makes sense it's going to be positive, right? Quadrant 4, cosine is positive. Cosine is adjacent over hypotenuse. Now, it makes sense also that we get out a value. You got a value, put in, you're going to get out an angle. Then you do the cosine of an angle, you're going to get out a value, right? So it makes sense. We don't even need to know what that angle is. We don't care. We don't care what that angle is. The angle whose sine is this, and then do the cosine of it. That's all there is to it. Okay, so here's some odd ones. These and this, again, you should do this no calculator. There's also 2 sides of a worksheet. Then there's 7 IXLs. No. I do have an IXL to add to the list, but
Did I get a worksheet for Jacob?
for who?
Jacob.
Yes. Maybe want to take one. Anybody see Andy? I think her what she was supposed to pick one up. Anybody see her for a while?
I do.
Who does? Okay. All right, now, here's what we're going to do. On this, the side that says inverse worksheet, we're going to skip a bunch of these now. Okay, where it says inverse worksheet, skip 1 and 2. Okay, skip 1 and 2. Skip all the ones that have the decimals in them, because all those are typed in your calculator, and those aren't going to be on the test, so I don't care about them. So all the decimal ones, 5, 6, 7, 8, 9, 10. Now, 9 you can, because that one actually you can do negative 0.5, negative 1/2. Think of that as negative 1/2, so you can do that one. But 5, 6, 7, 8, 9, 10, you skip all those. Backside, you can skip 4, 5, 6. Okay. You can skip 11 and 12. You can skip 4, 5, and 6 on that bottom section. Okay. All right. Oh yeah, we haven't done. Where do you see that one on?
7 and 8 on the back.
7 and 8. Yeah, just circle 7 and 8. We'll talk about it tomorrow. I haven't decided if I'm going to do those on the test. Probably not going to. So I don't think you have to worry about those. It's really easy, but I don't know. Okay, there you go. So 55 through 65 odd, which is some. I think those are. Yeah, those are ones where you just draw triangles. Okay, those are ones where we draw triangles like we were just doing. Okay, and then the worksheet ones are a mixture of the 2 different things we've been doing. This is pretty much it when it comes to the inverse trig functions that I want you to do for the test. Okay, if we can get through this worksheet with these problems here, we're good. We're good for the test.